So we're continuing to look at techniques of derivatives. We just looked at the product rule and the quotient rule, and those were easier ways to do the derivative than definitely the formal definition. And so let's just review what the product rule was. So let's say that we had y is equal to f of x times g of x. So if we wanted to take the derivative of this, we could denote it dy dx. Another way we could denote this is y prime. And recall, this wasn't just equal to the derivative of the first times the derivative of the second. This was equal to the derivative of the first, f prime of x, all times the second, g of x, plus the first, f of x, times the derivative of the second. So let's say that we had 2x minus 10 all times the quantity x cubed minus 6x minus 1. Okay, so we could do this by distributing and then using the general power rule for each term, or we can use this rule up here. And so if we choose this f of x function to be the first parentheses, 2x minus 10, and we let this g of x function be the second parentheses, x squared minus 6x minus 1. And we apply this rule. So the derivative of the first, so remember the general power rule, if we bring down the power, it's not shown, it's a 1, multiply it to the coefficient in front. So we have this 2 times 1, x, and then that 1 minus 1. Minus the derivative of a constant. So what was the derivative of 10? Minus 0. So derivative of a constant, recall, was 0. So it was our first derivative of our first times our second, g of x, x squared minus 6x minus 1. And then it said plus the first, which was our 2x minus 10, all times the derivative of the second. So general power rule, bring down our power. So we have 2x, and then take the derivative of minus 6x. So we have minus 6. So if we simplify, this is 2 times 1 is 2. X to the 1 minus 1, that's x to the 0. But anything x to the 0, that's just equal to 1. All times this piece, x squared minus 6x minus 1. Plus, I don't know if we want to distribute, let's just distribute and clean it up. Because a lot of times we're going to want to see when these are equal to 0. We're going to start graphing functions, and these derivatives are going to help us to graph functions. And so let's expand this and just simplify it. So 2x times 2x, this gives us 4x squared. 2x times negative 6, so this is minus 12x. Negative 10 times 2x, that's negative 20x. And negative 10 times negative 6, so plus 60. Let's distribute the 2. So we have 2x squared 2 times negative 6x is negative 12x. 2 times negative 1, so minus 2, plus 4x squared. I'm going to combine this negative 12x and negative 20x, so that's minus 32x plus 60. So 2x squared plus 4x squared, 6x squared. And then negative 12x minus 32x, so minus 44x. And then negative 2 plus 60. So that's plus 58. So technically, I think in this way, it would have been so much faster, right? If we had first expanded that and not used that chain rule. And so sometimes in math, there's multiple different ways to do things, and just being able to recognize what's the easiest way to go about that or this. And sometimes we don't choose that way, but and we should get the same answer. But let's just expand. Let's expand this. Or we could have said, okay, 2x minus 10 all times x squared minus 6x minus 1. Before we took the derivative, we could have expanded this. So this is 2x cubed. 2x times negative 6x is negative 12x squared. 2x times negative 1, so minus 2x. And then distribute the negative 10. So negative 10 times x squared is minus 10x squared. And negative 10 times negative 6x is plus 60x. And negative 10 times negative 1 is plus 10. So before we take the derivative, let's combine like terms. Notice that there is no other term that has an x cubed with it, so we're going to bring down the 2x cubed. We have a negative 12x squared minus a 10x squared, that's a negative 22x squared. A negative 2x plus 60x, so that's plus 58x. The one wrong. Oh, we haven't taken the derivative, sorry. Plus 10. And then, okay, it's plus 10. So now taking the derivative. So bring our power down front. We're going to have a cubed. X, subtract 1 from our power, so 3 minus 1. Minus our 22, bring our power down front, which is the square. Have x and subtract 1 from our power, so 2 minus 1. Derivative of 58x is just 58, so plus 58. And the derivative of a constant is 0. So simplify y prime equals 6x squared minus 44x plus 58. So there we just really had to distribute once instead of twice up here. Some questions on that? So what if it was y is equal to 10x squared minus x minus 2, quantity squared. Find the derivative of y. Okay, so hopefully by the end of the day, you guys can use the chain rule, which is a new method that I'm going to show you, or technique. But right now we don't know the chain rule, and so we could not just go forward and take the derivative of this. But we could rewrite it so we could take the derivative, right? So we could rewrite this so that this is, maybe I need that glove on, y equals, so the square out here is telling us just to rewrite this twice. So it's whatever's in the parentheses multiplied by itself. So from this point, we could either expand or we could use the product rule. Okay, so I'm not sure actually how you guys see yourself and where your name falls on the Zoom screen. But if you are the top half, so the top two, I don't know. See now, let me see how many students are in here. Okay, so I have 5 rows and 3 columns. So I'm not sure if that's how you guys see yourself. Is that how your grid is? No, that's not going to work then. I was going to say, okay, everybody in the top 2 rows, you're going to solve this by using the product rule. Everybody on the bottom 2 rows, you guys are going to solve this by expanding and then using the general power rule. So how about this? If you're on the top half of your screen, you're going to use the product rule. If you're on the bottom half of your screen, your tile, you're going to use the distribute and then use your general power rule. And I'm going to pause that while you have a moment to try. Okay, so the class just tried it, different methods, and we have 4 different answers that we have come up with, and maybe some even more out there. So I did it by expanding it, and some people did it, like I said, and some people used the product rule. So let me expand it because I want to see where I went wrong if I did go wrong. And so let's distribute. So I'm distributing this 10x squared to every single term inside the parentheses. So a 10x squared times a 10x squared is 100x to the 4th. A 10x squared times this negative 10x is a negative 100x cubed. This 10x squared times the negative 2 is negative 20x squared. Okay, so now I'm going to take this negative x.
Professor, shouldn't that 10x that you have there, shouldn't that just be x?
I have it as an x squared up here. Well, the oh, right here. Okay, you're right. Well, then that's where I went wrong. Don't look at my answer. Did everybody write it like that? Maybe some of you did write it like that, so maybe some of you didn't. Yeah. So that's exactly where I went wrong. So let me redo that then. Okay. So 10x squared times 10x squared, that's 100 x to the fourth. 10x squared times negative x, that is a negative 10x cubed. 10x squared times negative 2, so that gives us a negative 20x squared. So distribute negative x, we have negative x times 10 x squared, so this is negative 10x cubed. Negative x times negative x, that's plus x squared. Negative x times negative 2, this gives us plus 2x. Distribute the negative 2 to every single term. So negative 2 times 10x squared is negative 20x squared. Negative 2 times negative x, so that's plus 2x. And then negative 2 times negative 2, that's a plus 4. So rewriting it, combining like terms, there's no other x to the fourth term, so we have 100x to the fourth minus a 10x cubed minus a 10x cubed, which is minus a 20x cubed. We have a negative 20x squared plus an x squared is negative 19x squared. And then minus 20x squared, so that's negative 39x squared. Then we just have plus 2x. And then we have a plus 4. Oops, we have a 2x plus a 2x, which is a 4x. And that was not our derivative yet, so let me get rid of that prime. So now taking the derivative, bring our power down front, 4 times 100, so that's 400, x, subtract 1 from our power, so this is cubed, minus, bring our power down front, so 3 times the number in front, 20 is 60. Subtract 1 from our power, we now have an x squared. Minus 2 times the number in front, 39, is 78. Subtract 1 from our power, we get just an x. Plus the derivative of 4x is 4, and the derivative of 4, that goes away. So look at that. And she used the product rule. Okay, so hopefully those that didn't get that saw where you did your error if you had expanded it. Okay, so any questions before we move on? So we're going to jump into the chain rule now and why we would want to use the chain rule. But actually, before we do that, let's review a little bit on compositions of functions. So composition. of two functions. Let's say f of x is equal to, oh well, doesn't matter. Let's call it f of x and g of x because I want to do notation first. So this is written as f with a little circle g and parentheses around that, and then x. But this really means f parentheses of g of x. So you're basically plugging in g of x wherever you see an x in f of x. So order matters here, which function goes where. So let's just kind of review. Given two functions, let's take the composition of those two functions. So you guys have pretty much been doing this already in class. So part of that definition, formal definition of a derivative, right, was looking at plugging in some function that's called g of x plus h. And maybe f of x is equal to x squared minus 2x plus 3. So if it said find f of g of x, so again, we can rewrite it. I think the other notation means more when it looks like this. Or another way to write that is f of, we're going to go in here and we're going to rewrite what the equation g of x is, which is just x plus h. So wherever we see an x, an f of x, we're going to replace it with this whole quantity x plus h. So go in, let's plug it, put in parentheses wherever we see an x. So we have an x, put parentheses, we're going to square that, minus a 2 times we see an x, so just put parentheses for now, plus 3. So replace wherever you have a parentheses with x plus h. And I'm not going to expand this because I want to kind of get to the point where we're noticing what is the inner function, what is the outer function. So notice here the outer function is this f of x. And this g of x is our inner function. So because I did that, I'm not going to change it and say, let's look at the opposite direction. I'm going to blow this up a little bit so I can have thicker pens. So given that f of x, let's say, is equal to x over 8 plus 7, and g of x this is equal to 6x minus 1. So find f of g of x. So we're just going to go in wherever we see an x in f of x. We're going to replace that x with a whole expression, 6x minus 1. And so here we see an x. I'm going to just put parentheses for now, all over 8 plus 7. And now go in wherever we saw an x, let's replace that in our parentheses with 6x minus 1. So we can simplify a little bit, but again, we don't need to for now. Part B though, if it said do the opposite direction, if it said find g of f of x, so this is saying find g of f of x, but f of x, that's this whole thing, x over 8 plus 7. So this is saying go and plug in this whole expression, x over 8 plus 7, this f of x function, wherever you see an x in g of x. So we have 6, I see an x there, it's times, I'm going to put a bigger parenthesis so I can fit this, minus 1. So we're going to replace this parentheses with that whole expression, x over 8 plus 7. This is not going to give us the exact same thing up here. I don't want that to be open. Okay, so technically we want to be able to identify what's the inner function, what's the outer function, and that's part of the chain rule, is looking at taking the derivative of composition of functions. So pretty much all of our functions can pretty much be written as a composition of multiple functions. For instance, if you have h of x is equal to the square root of 2x minus 1 underneath the radical, and you want to find some function f of x and some function g of x such that h of x could be rewritten as a composition of those two, f of g of x. So really, if you are doing these compositions and you're trying to break it down and what is the inner piece, it's going to be stuff like what is underneath the radical, or things that could be rewritten to some power. So if you had, like at that beginning when we had that x squared minus x, or 10x squared minus x plus 2, or whatever it was, quantity squared, what was inside that whole polynomial inside, we could call the inner function. And so our inner function, let's think of it as what's inside or underneath the radical. So let's call that g of x. So g of x, let it be 2x minus 1. So basically, you're going to let f of x be the outer function. Well, that outer function has that square root. We need that square root in there. And we want to put an x wherever we chose to be, whatever we chose to be g of x. So I'm going to say the square root of x. So basically, if I go in and take this g of x and I go back in and plug it in wherever I see an x here, that would give me my h of x. I don't know why it keeps doing that. So maybe if h of x was 1 over 6x cubed minus 10x squared plus 5. Find some f of x and g of x such that h of x equals f of g of x. So if anything was repeating in there, I would choose that to be u. But notice that I don't know this. We can't rewrite this, that we bring these terms up because there's more than one term here. So there were some times where we manipulated it, we brought terms up and we rewrote the exponents as negative. Well, we can't do it there. So if we choose g of x to be this whole denominator, then f of x, so basically it's this whole thing except wherever we see that what we chose g of x to be, that's where we're putting the x. So this would be 1 over, I see all of my g of x there, x. So if y is equal to x to the 1/2 power minus 3, all of that I just said was in parentheses. So x to the 1/2 minus 3, that quantity in parentheses, and then that whole thing is squared. And then you have plus what you had in parentheses over here, you have here. So x to the 1/2 minus 3, and your parentheses plus 5. So we want to find f of x. Let's do a different color. And g of x. Such that y is equal to f of g of x. Well, if you see any expression repeating itself, that's a clue that that should be what your inner function is. And so our g of x, that should be just the x to the 1/2 minus 3. And then that would tell us our f of x function. Wherever we see an x, it's going to bother me. So wherever we see an x, we're going to, wherever we see that expression that we let g of x, we're going to let be an x. And so here I see this whole expression. So this will be x, and then it's going to be squared. Plus, I see this whole expression, I chose g of x, so I'm going to have that be x. And then I have this plus 5. So if we took this, what was in parentheses, plugged it in wherever we saw an x, an f of x, we would get back what y is. Okay, so that's a good spot to stop and take a break. I was going to give you the chain rule first, but maybe, or maybe actually I will give you the chain rule first, because maybe since you would have heard it, and when we come back in 15 minutes, you'll hear it again.
Professor?
So, yes.
I just have a question real quick. So after we state what g of x is, for when we do the f of x, is that just like replacing what g of x was with an x? I'm not sure I understand that part.
That's exactly right, Melissa. So wherever
Okay.
whatever you chose g of x, then replace that as x for your f of x function. And so notice that we did that for our denominator here also. That's what we chose g of x to be. And so we just replaced that with an x for our f of x function. But we have to put everything else in there that wasn't there before.
Okay.
So go back up to that square root function. That's what we chose g of x is. And so f of x was that square root, and then whatever that g of x function was the x.
Okay, perfect.
And so this is helpful to figure out what's the inner function and outer function, because when we take the derivative of these, it's going to fall out. So right now, those functions that I gave you, we don't know how to take the derivative of those. But now with these tools, or this formula, you will be able to take the derivative. So this is the chain rule. So if f of x and g of x are both differentiable functions, then if, let's say, y is equal to the composition f of g of x, I'm just going to change again colors just so you see it. then the derivative of y. So y prime is equal to, so it's the derivative of the outer function. So we're going to look at f prime, but after that we take that derivative of the outer function, we're going to replace x with wherever a g of x. And then we're going to multiply this all times the derivative of the inner function, g prime of x. So derivative of the outer function of the inner function times the derivative of the outer. Outer function. Okay, so there's multiple rules that you should have down, and those maybe are ones that you want to just make some flashcards to quiz yourself. So the product rule, the quotient rule, the chain rule. Okay, so that is a good spot to take a break. And then we'll come back and we'll do some examples. So we just looked at what the rule was for the derivative of the chain rule, using the chain rule. And now we're going to look at the chain rule, that same rule, but written in Leibniz notation. So it says if y is a function and y equals f of u, and u is a function of x, say u equals g of x, that would say then y, which is equal to f of u, is also equal to f of g of x. And if we were taking the derivative of y, dy dx is equal to the derivative of y with respect to u times the derivative of u with respect to x dx. Or like we just mentioned, y prime, other notation is equal to f prime, the derivative of the outer function, plugging in the original g of x, wherever we see an x there, times the derivative of the inner function. Okay, so let's look at an example. And let's say y is equal to 2x cubed plus 9x all raised to the 5th power. So we could do this using the process that we've been learning. We could take 2x cubed plus 9x and multiply that out 5 times, but that's going to take a lot of work. And so being able to figure out what is our inner function. And so if we let that inner function g of x let that be what's inside the parentheses. So we're going to let g of x be 2x cubed plus 9x. And then let f of x, the outer function, well, that's going to be, we're going to put in an x wherever we see what we chose g of x to be. And then we need to write everything else down. And so we have this parentheses here, all raised to the 5th power. So we can do this in pieces, and we're going to get good enough at this where we're not going to be doing it in pieces, but let's do it in pieces. Let's look at, we need to know what the derivative of our outer function is. So let's look at the derivative of f prime of x. And so if we bring down that general power, 5x, and then subtract 1, so 5x to the 4th. So the derivative of these inner and outer functions are not bad at all. For some reason, it keeps on wanting to pull that up. Okay. So g of x, or g prime of x, the derivative of g of x, the inner function, bring our power down front, 3, multiply it to the coefficient in front. So we have 6x, subtract 1 from our power, we get 2, plus the derivative of 9x is just 9. Okay, so the derivative of y prime is equal to the derivative of the outer. So this is 5 of our original function g of x. So let me just put g of x there for a second. Raised to the 4th power times the derivative of g of x. Well, the derivative of g of x is this 6x squared plus 9. So y prime is equal to 5 times, plug in g of x right here. So g of x was up here. So that was the 2x cubed plus 9x. That is all raised to the 4th. All times the derivative of g of x, which is 6x squared plus 9. Okay, so we could have done this. We could have done this the other way. So where dy dx is equal to dy du all times du dx. That's our original function. So y was equal to 2x cubed plus 9x to the fifth. Y was equal to okay, so we want our inner function to be what u is. And so in this case, the inner function, because remember u or g of x, u is equal to 2x cubed plus 9x. And then our outer function, which is, we're going to say y equals u to the fifth. Or we can let y is equal to f of u. So if we look at the derivative of dy du, that's what this is saying. Find the derivative of dy du. So dy du, so taking the derivative of this, we know we get back 5u to the fourth. And it wants the derivative of u with respect to x. So if we take the derivative of u right here with respect to x, this is bringing in our power down front and multiplying it by the coefficient 2. So we get 2 times 3 is 6. X, subtract 1 from our power, we get a square. Plus 9 times our power of 1, which is 9. Subtract 1 from our power, we get an exponent of 0. That's just 1. The problem is we need to go back and we need to substitute in what y is. I'm sorry, what u is. U is this though. And so we get dy du is equal to 5 all times u, which was this whole stuff, 2x cubed plus 9x. This is all raised to the fourth power, all times this 6x squared plus 9x. I'm sorry, just 6x squared plus 9. Which is the same thing we got before. So either way, same results. So sometimes just getting used to that Leibniz notation is good because it's helpful to plug in sometimes that you're taking the derivative, you haven't taken the derivative yet, and you're going to go back and show that work because you'll see that these are going to get a little more complicated where there's a lot of compositions going on, multiple, more than 2. And so we have to do layer upon layer upon layer. But for now, let's just concentrate on a little simpler ones. So let's say you have f of x is equal to 8 all times the square root. And underneath that square root is 4x squared plus 7. And it wants us to find the derivative of each function defined as follows. So find the derivative. So we need the outer function, we want the inner function. So usually going to find the inner piece is easier first. And so let us choose, I don't know what we want to call it, g of x. Or we can call it u is 4x squared plus 7. So we can say, well, then y is the same thing as f of u. So looking at it, we have an 8 here, and then we have a square root. And then replace what we chose g of x or u to be. So derivative with respect to u, so the derivative of g of x is equal to, well, 4x squared, the derivative of that is 8x, and the derivative of 7, the constant, is 0. And the derivative of y which actually, before we can take that derivative of u with respect to, sorry, derivative with y with respect to, this should be dy over du. With respect to u's, we need to rewrite this as 8u, and so rewrite it in exponential form. So the square root is the same thing as the 1/2 power. So in that form, you can see we're bringing our power down front. So 8 times 1/2 u, and then we're subtracting 1 from that power. So 1/2 minus 1. So I'm going to write that 1 in as a common denominator, 2 over 2. So dy du is equal to 8 times 1/2, or 4. U to the 1/2 minus 2/2 is negative 1/2. Let's just rewrite it with a positive exponent. And so that negative exponent is only with a u, so the 4 is going to stay in the numerator, all over u to the 1/2. And then in radical form is 4 all over square root of u. So dy dx is equal to dy du all times du dx. So dy du, darn it, I need to close those down. So dy du is this, which is 4 all over the square root of u, all times du dx, which is right here, 8x. So simplify it a little bit, and we don't want this in terms of both x and u, so we have to go back in and rewrite in this form what u is. U is this 4x squared plus 7. So this is 4 all over the square root of 4x squared plus 7. And this times 8x, we can multiply that in the numerator. So this is the same thing, and this 4 times 8x, so 4 times 8 is 32x, all over the square root of 4x squared plus 7. So that was with this method. But if we had written it in the form of y prime equals f prime of g of x times g prime of x. So using that notation, so in our case, the derivative of the outer is this piece. So that is 4 square root of the inner u, which is 4x squared plus 7, times the derivative of the outer, which we said was 8x. So we got 32x all over the square root of 4x squared plus 7. Okay, so we will look at more examples tomorrow, not tomorrow, Wednesday, using the chain rule, and then we might look at the derivatives of exponentials. But so far we just started 4.3. You should be able to do probably at least half of the homework in there.